Hello, my name is Ilya Alexyenko. I'm a PhD student at Aarhus University, and I want to present a paper called Analysis of voxel-based 3D object detection methods efficiency for real-time embedded systems. In this presentation, we will go through introduction, related work, we will define depth zones and experiments, discuss DNet's inference speed problems, and go to conclusions and future work. 2D object detection methods operate on camera images and have to find objects in those images, but 3D object detection methods have to find positions of objects relatively to a nego object. As an example is an autonomous car, and also a pose of these objects as a rotation around vertical axis. So the best 3D object detection methods in combination of both speed and detection accuracy operate on LiDAR point clouds, and even though they can be real-time in desktop GPUs, if you try to apply it for embedded systems which are slower and have lower amount of memory, those methods can be not real-time methods. If you want to define the real-time methods for LiDAR-based 3D object detection, usually it's based on the LiDAR operation rate, which is either 10 or 20 Hz, and even if a method has higher FPS, it won't be able to process data at faster than LiDAR operation rate. So, but there is a problem that usually you don't only need to find a position of an object, you have to do something with that, as to control a robot or a car, and it can be that there is another deep learning method after 3D object detection, and it still have to spend time on it. So having a faster method than a LiDAR operation rate can be still beneficial. In Visual LiDAR-based 3D object detection and tracking for embedded systems paper, they propose a method that operates with 10 frames per second on NVIDIA Jetson AGX Xavier embedded system, which is good, but if we want to combine it with something that will process these positions of these objects, it will be not enough to be faster than the LiDAR operation rate. So many optimization techniques for 3D object detection come from the more mature 2D object detection or image classification case that include knowledge distillation, layer pruning, and network quantization. We select point pillars as one of the fastest 3D object detection methods and DNet as the more accurate but slower version of point pillars for our research. So point pillars takes a point cloud as an input that then selects a subscene of it to split it into an equal cuboid, which is called voxels. And for a point pillar case, it's pillars, which means that along vertical axis there is only one pillar. It means that we have a two-dimensional grid of points. And then this grid is processed by a pillar feature net to create a pseudo image that is then can be processed by a regular 2D convolutional neural network to create predictions of positions and rotations of target objects. So DNet is pretty similar to point pillars, but it has stacked triple attention models for pillar feature extraction, and it has a coarse to fine regression model instead of the backbone CNN, which is a point pillar's backbone CNN as a coarse regression part, and in addition to it we have a fine regression model that takes features and outputs of a coarse model to create better predictions. And here you can see a figure of a triple attention model that uses point-wise, channel-wise, and voxel-wise attention to create better features of each pillar. So this works operate on ICETCI dataset, which means that we have to consider only a frontal part of the point cloud, because ICETCI dataset has objects has ground truth objects only in a part that can be visible by image. So this subscene that is selected by our voxel-based methods, we can split it into two parts, which is a near subscene with the green color and a far subscene with the blue color. And as you can see, a near subscene has much more points than a far subscene. And when we pass this half-size subscene to a network as TNet or point pillars, it will reduce the pseudo-image size twice, so meaning that it will have less data to process and it should be faster. So in our experiments, we train models with pillar sizes 16, 20, 24, 28, which means that if we have a pillar size 16, it's a pillar of 0.16 meters for x and y dimensions, and around 4 meters for a vertical z dimension. And then we train those models on both near and full subscenes separately, and on two sets of classes. It's car and pedestrian plus cyclist. Meaning we have only one model for both pedestrian and cyclist. Then we evaluate all of those models on both near and full subscene, meaning that each model will be evaluated on a subscene it was trained on and on another subscene. In this figure, you can find results of evaluation of point pillars and TNet models on full and near subscenes, where we split it by class and object difficulty. And for each model we named 16, 20, 24, and 28, it means that it's trained on a full subscene and has a corresponding voxel size. And if it has a suffix of near, it means that it was trained on a near subscene. And we evaluate those models on both near and full subscene and place those values on the plot. And the colored line describes the difference between values, between 3D average precision of those evaluation. And we have in all cases, we have a better result for a full evaluation, and meaning that we can just say the difference between full and near is this amount, which is described by the line. From this graph, you can see that near models operate on the same 3D average precision level as corresponding full models. And sometimes it's even better, as for pedestrian case, 16 near model is the best along all near and full models, which means that these networks try to find representations of far objects by applying representations of near objects to it. And even though 16 model had more data to be trained on, 16 near model outperforms it. If we compare FPS evaluation of those models on a desktop GPU 1080 Ti and embedded systems Xavier and TX2, we can see that we can achieve on average 25% increase in FPS for a desktop GPU, 40% for a Xavier embedded system, and 60% for a less powerful TX2 embedded system. So when we evaluated TNet, we found a problem between its stated inference speed compared to point pillars and what we had compared to 2-point pillars. And then during a code investigation, we found that in a coarse-to-fine regression model, functions predict coarse and predict refine are called in one inference step, but both of them increase total inference count number by batch size, which means that for one inference step we have twice higher number of inference count and which is used during the average forward time calculation. So, in conclusion, point pillars and TNet fail to detect small distant objects due to the sparsity of their point representations, models that are trained on near objects achieve similar or better performance compared to those trained on all objects in the full scene, which means that these models learn appearance representation mostly from near objects and then try to apply them on far objects. Considerable part of computation is focused on locations of the scenes that do not contribute with successful detection, and this means that we can achieve a speed up of 40 to 60% on embedded systems by restriction operation to near objects while not sacrificing much in performance. For future work, application of a pair of methods where one operates on the far subscene and another one operates on the near subscene can lead to an increase in both detection accuracy and inference speed. This work has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 871449 OpenDR. This publication reflects the outer views only. The European Commission is not responsible for any use that may be made of the information it contains. Thank you for your attention.